It's often said in places in the world where you have to toot your horn to stop accidents that, the person who has an accident wasn't tooting often enough and loud enough. And that was the problem. And the problem with this bit bonding wasn't the fact that there were engineers down in the voice systems and so on doing things on the circuit. It's the fact that you didn't cross all your toes and all your fingers enough and weren't genuflecting often enough. It's all your fault. Equally silly in terms of attribution and engineering. But you're right, trying to fit a more stringent application on top of a system engineered for something completely different was always going to be difficult. But the point was the only way you got better speed out of this system, at least at that level, scunging voice circuits, was to try and sort of sticky tape the voice circuits together.
You're listening to Ping, a podcast by APNIC discussing all things related to measuring the internet. I'm your host, George Michelson. This time, I'm talking to Geoff Huston from APNIC Labs again, in his regular monthly spot on Ping. Geoff and I talked about making things go faster than the visible bandwidth of a single link. How is that even possible? We've been using the same basic techniques to manage this problem since the dawn of digital communication. We send different bits of the data stream down different links and reconstruct it at the other side. When you come down to it, there isn't really a good alternative, but this introduces a problem of sequencing. What do you do when the bits arrive out of order? Or worse yet, not at all. Different protocols and different layers in the protocol stack have now come to the fore in this engineering problem. Geoff reviews some of the past history and the kinds of problem we're now hitting as the underlying network gets faster and faster. Geoff, welcome back to Ping. What shall we talk about this time?
Hi, George. Look, it's good to be back. Today, I actually want to talk about how can you make things go faster than the components underneath them?
Throw them harder.
Yeah, blow at it harder. How do you kind of extract greater performance than any individual element can? And this is not a problem that's unique to networking. I remember in the days of mainframe computers, which, there are still a few of them still around, I guess. And the way they kind of solved the problem of how do you make a bigger, faster computer was kind of put two of them together, double the speed. Now, it's not linear speed, but it's certainly double the throughput.
Do you remember Seymour Cray's comment about people who were ganging up processors? He said, would you rather have 2 oxen or 1 million chickens pulling your plow? So there's kind of history here that scaling up by doing more at the same time, there's some skepticism.
I have news for Seymour. I really do.
Yeah.
And the answer is a retrospective high from 1 million chicken world because, we went there.
Let's put it back in the networking context, though. What about a network and the limit of speed that you've got available? What is it here that's allowing you to get faster than you think you can?
Well, it's exactly the same approach with computing. That, in essence, if you're trying to get more jobs through a computer and not necessarily this job to go faster, but just more jobs per hour, then assigning more computers to the problem, more processors, etc., going parallel actually solves your problem. Now, in some ways, it's not the most efficient solution. Typically, when you scale up, you get benefits that are way in excess of linear. And simply adding more, +1, +1, +1, is more of a linear problem. It doesn't make the unit costs any cheaper, but it does solve your problem. Now, we've encountered this in networking probably from the year dot. And by dot, I mean, somewhere around late 70s, early 80s. We started building computer networks leeching parasitically on the back of telephone networks. And at the time, the telephone networks were just going through a tranche of digitalization, that rather than carrying analog sort of streams of signal for each voice conversation, we actually digitized them. And inside the telephone network, if you could peel apart all these virtual switching layers, what you'd find is that each conversation was actually a stream of bits, right?
Yeah.
And the way the human voice works, most human voices, is that as long as kind of the basic aim is intelligibility and clarity, you can digitize a human voice stream by doing 8,000 samples a second.
really quite a small number when you think about it. It's not a massive amount of sampling, is it?
Well, George, I don't know about your soprano voice, but mine wouldn't even make 8 kilohertz, so it's not bad.
Yeah, the thing is, both of us worked at the tail end of this process in telecommunications related roles. I was working for a minor player while you worked for the major player, the former monopoly telco. And we actually exploited a niche in the market of ideas here. You, the big guys, you were meant to use the full width of a voice channel to send a message between 2 points, long distance, because otherwise there would be too much quality loss. This weird idea called the QDU. And we, as the on-top carrier, we were allowed to compress and send either 2 or 4 voices down the same channel. And it was a really funny business working out.
It was weird, wasn't it?
Oh, the quality was not good at the 4-channel end of things.
Well, so yes, I was getting to 8,000 samples a second. And in the original spec, each sample effectively said, I'll give you one of 256 different volume levels. And so every 8,000th of a second, it sent an 8-bit value, which was the volume at that point. And that would actually accurately reproduce a signal of anything up to 4 kilohertz. And your best soprano voice and mine can't go above about 3.9 kilohertz. So it kind of worked, right? But the issue is, yes, you can, with enough cleverness in the way you encode it and decode it, cram more in. And as soon as sort of this standard came along, then along came 7 bits at 8,000 hertz, probably enough used by the Americans, 56 kilobits. And then came 4 bits at 8,000 kilohertz, which is 2-to-1 compression. And they even got this further, actually getting down to 2 bits at 8,000 hertz, which is one of the higher compression algorithms. And they used that in the mobile phone industry and just sort of squished the voice down to the point where, as you say, it was pretty heavily distorted.
Yeah.
But by God, it made use of the network. Okay.
We stopped talking about QDUs very rapidly in this world. We stopped actually having some idea of the amount of nastiness in the voice call we would tolerate, because we realized people would actually tolerate a hell of a lot more nastiness for a cheaper call.
The telco benchmark, I think, was 13 QDUs for any conversation, including international, which was a bit of a joke, really. But I come back to our story. You see, we started networking as an overlay across basic circuitry, which was, I'll strap up A to B and I'll nail a voice call, because we are a voice switching network. And if you lived in America, that was a 56 kilobit per second line, 7 bits and 8,000 cycles a second. Oddly enough, because of framing and signaling in the sort of European/British oriented world that included Australia, you got 48 kilobits because they stole 2 bits on each frame for signaling and everything else. So the fastest you could go from A to B was 48 kilobits. Interesting. I want to go faster. Ooh, fascinating. What are we going to do? Now, I can't give you a single 96 kilobit per second circuit because I don't have one. I can give you 2 48 kilobit per second circuits. Great. Okay, what can I do with them?
How do you manage having 2 things that are kind of half what you want? Can you use them in a way to make it look like one thing?
Well, that was the first kind of approach, and it persisted for quite some time in the industry, but only really worked at kilobit per second rates, which was called bonding, where you actually look at these 2 circuits and you assume, fingers crossed, toes crossed, face in the appropriate direction and genuflect many times, that both circuits will remain absolutely stable. And then you go with your bits, 1010, you go AB, 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 and hope that the other end locks in and that it sort of puts the bits back together in precisely the right order.
Yeah, because an AABB moment isn't doing you any favours whatsoever here, right? You need to be able to reliably sequence everything you write down this.
Yes, I remember we did a link from Melbourne to Perth for about a year and a half on bonded 64K circuits. We managed to get it as high as 256 kilobits per second, but beyond that, it's sort of not going to go there. So bit level bonding kind of works, but the underlying fabric needs to be absolutely rock steady because otherwise the receiver is kind of clueless.
Yeah. And you have to also remember this is technology that was never ever constructed and built out to be clean for digital. It was built for voice. It was built for analog signaling. And an engineer in a switching fabric could have reasons that he needs to randomly put another 200 meters of cable between 2 points in this system for a number of reasons. These two things might no longer actually have the same imaginary length between A and B. There are any number of reasons they could get out of sync with each other.
You know, it's often said in places in the world where you have to toot your horn to stop accidents that, you know, the person who has an accident wasn't tooting often enough and loud enough. And that was the problem. You know, and the problem with this bit bonding wasn't the fact that there were engineers down in the voice systems and so on doing things on the circuits. It's the fact that you didn't cross all your toes and all your fingers enough and weren't genuflecting often enough.
Yeah.
It's all your fault. Yeah. Equally silly in terms of attribution and engineering. But you're right, you know, trying to fit a more stringent application on top of a system engineered for something completely different was always going to be difficult. But the point was the only way you got better speed out of this system, at least at that level, scunging voice circuits, was to try and sort of sticky tape the voice circuits together.
Yeah, use them in a way that although you absolutely knew at some lower level these are four discretely different things, you treated them through infrastructure costs that you had to wear, both ends, you treated them as one fatter pipe, 4 times the width, probably losing a bit of overhead managing this thing, so maybe 3 and a bit times better, but you
can actually get all 4 if you used the technique in a router rather than in a bit level driver. So instead of down at the line driver circuit, you're going A, B, A, B. Christ, I hope this is working. A, B. Was it A or was it B? A, B. Oops. Instead, up at the router, you have interface A and interface B, and your currency is now packets.
Right.
And so you can take these individual packets that you're switching through the router, and a naive person, a very naive person, and silly as it turns out, might simply go, you're all destined to the same next hop. You're all going to go to the B end, whatever your ultimate destination would be. Packet A, interface 1. Packet B, interface 2. 1, 2, 1, 2, 1, 2. And because the maximum size of packets is actually pretty low, 1,500 bytes or so, the two systems won't get out of order that much. You know, you won't be transmitting a huge packet for 3 hours down one line while the other line is taking all the load. You won't be doing that. When you do sort of packet level, you know, alternate switching, things don't get out of order too much, but they do get out of order, right?
So there is a cost consequence emerging here.
Well, let's think about now going up a level in the protocol stack to our good old friend TCP. You see, TCP is the piece of magic. So far, when I'm doing AB, packets might get out of order, I have violated none of the rules of IP. You know, the golden rule. It's a datagram network. A, I'm allowed to drop packets. What? Of course I am. Every packet's an adventure. B, I'm allowed to reorder them. Really? Yes,
Yep.
the datagram
No
network.
guarantee of order of delivery if you're just at the IP level.
Yeah, no guarantee that they won't get duplicated. All kinds of things happen at IP, and all of them are legal. All of them. It's TCP's job to try and make sense and say, here's an ordered sequence of packets, 1, 2, 3, 4, 5, 6. And present them to the application correctly. It's the engines at either end of this network connection that have all the work to do, right? So they're sitting there analyzing individual TCP packets that come to them going, I guess you're the next one in order. That's good. I'll acknowledge it. Tick, send back an ACK. You know, I've got this packet. And that's how you kind of reassemble things. And when you go 1, 2, 4, 5, 6, it's kind of, oh, I'm missing number 3. Hello. The last good packet I got was packet 2. Let's resume at packet 2 and press on, which seems a bit useless, but it kind of works, right?
Well, it kind of works, but it incurs this problem that it's almost like you throw away all the subsequent acts. If only you could come up with an engine that said, I'm going to hang on to things a little bit longer and maybe ask just for the hole to be filled in. You could do a little better, but that means you've got to hang on to things. You're adding delay.
Well, there's an odd part about all of this. So in TCP, an out of order packet, a packet that kind of isn't the next one in sequence, is treated as, well, I'll hang on to it, but I'm going to send you back an indication that there are lost packets. So when I receive packets 1, 2, 4, 5, 6, the real information I need to convey back to you is I lost it at packet 3. I was expecting 3. I got 2, but I didn't get 3. Whatever else you've sent, I'm missing 3. So what I do is I ACK number 2 for 4, 5, 6. So the ACK stream goes 1, ACK, 2, ACK. When I receive 4, I go 2, ACK. When I receive 5, I go 2, ACK. When I receive 6, I'm shouting at you, 2, ACK.
Doesn't make 3 magically appear.
Well, it does. The theory is because you keep a copy of everything you sent until it gets ACK, realize eventually, because, I'm getting a bit anxious at this point, that 3 hasn't been ACKed. So you move back your send pointer and you send 3. Now, if you just send 3 and nothing else in this sort of theoretical model, I put 3 in the hole that I just have.
Yeah.
And then I notice that I received 3, and I've got 4, and I've got 5, and I've got 6. ACK 6.
Right. So you can fill in the gap at the cost of keeping enough buffer to hold those packets.
Right.
And there's a bit of delay here facing upwards. You can't pass things on in clean conscience till that hole has been filled.
Right. So you need a fair deal of knowledge and timer sensitivity that, quite frankly, doesn't exist very much. So out-of-order packets are a nightmare. TCP gets horrendously confused. They cost because out-of-order packets are assumed to be lost packets, and in the worst case, go back at the lost point and send everything again.
Yeah. So I figure, Geoff, based on your line of reasoning, that where we're going with this is, well, if you think you get out-of-order packets when you've got one thing underneath you, what do you think happens when you've got 2 or 3 or 4, right? Is that where we're going?
Well, that's part of it. The problem gets magnificently worse for TCP, right? Magnificently worse. Because once you get 3 duplicate ACKs in TCP, the conventional TCP, the TCP of the biblical age says, that's catastrophic. Shut down everything, start afresh, let's do a slow start again. I was going to gigabit per second. No, you're not anymore. Close that stuff down, shut down, because I've just had 3 duplicate ACKs, so this is a disaster. We'll start from one packet again.
3 in a row, hello, that's not good.
So you were ganging together 4 lines, and if you lost one of the packets on one of the lines, you guaranteed you were going to get 3 duplicate ACKs if you're just doing it that way. So you think about this and you think something's missing and this is not working for equal cost multipath. What can we do?
Equal cost multipath. That's kind of the name for the situation when you've got 4 things and you think they're pretty much the same weight and you think they're the same delay and you want to treat them as splits of something you're going to gang up together to make a fatter unit to get between 2 places.
I've got 4 64K circuits and I want to mimic a quarter of a meg. I've got 4 10 gig circuits and I want to mimic 40 gig.
Yeah.
Same problem. Just 1,000 times faster or a million, but same problem.
So equal cost multipath. That's a great phrase. I'm going to hang on to that.
Well, fair enough. And the issue is, what can you do about it? Now, before I talk about going on with TCP, I just want to talk for a second about that evil word, fragmentation, IP fragmentation.
Oh, we have talked about that. We have talked about that so many times on Pingja, particularly about IPv6 for a very specific reason.
Evil, particularly if you've got your V6 glasses on your head. Yes, very evil. But oddly enough, it is actually amazingly resilient for packet reordering.
Wait, run that one again. Frags are bad, but
when I effectively take a set of frags of one packet. So I have a single packet and I apply the fragmentation dicer and I slice and dice this packet and then I send them to you in purely random order. No attempt to do any kind of ordering. None.
Whoa.
And as long as I send them continuously, I sort of push it out through all my paths simultaneously, the other end goes yummy, 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 not a problem. Ogle, 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 high upper layer, here's the completed packet.
So It'll deduplicate them, it'll reorder them, and it'll pass up a valid packet if you just do your worst and chuck the fragments out there.
Right, because there's a piece of information in an IP fragment that isn't necessarily there in a TCP fragment. And it's actually, if you will, the fragment's address within the packet that you just sliced and diced. Hi, I'm fragment number 3. I'm fragment number 7. I'm fragment number 2.
The fragment knows where it fits in the entire packet. You know you're building up a picture of what you've got and what you're missing.
Yes. And if you actually had used that kind of sequencing addressing in TCP would be equally resilient, but we didn't do that. We used a single sequence counter, which doesn't give you much information at all. Whereas in IP fragments, actually used 2. I'm packet number N of M. Fascinating. So one of the ways to get around this is to fragment everything.
I don't think you're really going there.
I'm not. The other way of doing this actually is to make, I suppose, an assumption which the purists of the world, and I think the last purist died in about 1980, the purists of the world would say is a layer violation. You reach in and look at the header of the transport session. Oh, look, there's a source address, a destination address, that's in IP. There's a source port and a destination port. No, that's a TCP or UDP construct. And there's a protocol number. I'm TCP or I'm UDP. So the protocol number, the 2 port numbers, and the 2 IP addresses are actually unique signature of a session.
Yeah.
So if you and I are having 2 conversations simultaneously, one of those values would be different.
Right.
Probably one of the port numbers.
So the packets arrive at the air quotes same place because the same source and destination address are on it. And it's possible one of the port numbers is the same port number, but one of the other ones is going to be different because someone has said, give me a random port to send some stuff. You get a different random number.
So let's say I take this value. Now that's 2 addresses, 32 bits, 2 port numbers. That's another 32 bits, yes, 16 plus 16 plus 30, sorry, it's 232, 64. I can't add the stuff this evening. 64 plus 16 and 1, 81 bits. And I hash it. Let's say I've got 4 lines, 0, 1, 2, and 3. I hash this into a value between 0 and 3.
We're going to have to start calling this podcast the Hash Podcast because you were talking about hashes in the context of NSEC3 DNS last time, Geoff. Hashes are unbelievably powerful and useful, aren't they?
We should pay mathematicians more money. They're brilliant people.
Yep.
The lifeblood of civilization. I speak as a reformed mathematician.
I was just about to say, what is your degree classification? So you take the 4 unique values, you get an 81-bit number, and you generate a hash from it.
And the same sort of values in that 81 bits will always give you the same hash. Always.
Right.
But a random selection of ports and destination addresses, etc., will give you a pretty good distribution across your 0 to 3 across your 4 port numbers. So what this means, oddly enough, is if you can do this quickly, and it's really easy to do, take 81 bits and hash them, return back basically 2 bits, with 0 through 4, however many I want, that's the selection, which interface to use. Every session will go down the same interface all the time.
Wait. So if I'm trying to load balance things happening through me, and I've got a cheap way of making 4 values in 2 bits, pretty much cover an even distribution of 00011011.
Yep.
And the other thing you just said, the other part of this deal is that if I am a particular pattern of source, destination, random port, specific port, I always wind up in the same 2-bit value, which means if you're using that to address the port, I will always go down the same line, always.
Right. So if I've got equal cost multipath across 4 10 gig paths, a single session will only ever see a 10 gig path. But if I've got a whole bunch of traffic going down these 4 by 10 gig circuits, which are equal cost multipath, a bunch of traffic, the aggregate throughput, I can push up to 40 gig.
You're moving the goalposts a little. I mean, not in a bad way. The net outcome is beneficial. You make efficient use of all the bandwidth you've got available, but no individual person for one TCP session is getting 40 gig. That ain't going to happen.
And that's a very magic phrase you just said there, George. No individual TCP session can get more than one of the individual paths in my path group.
On the other hand, you are using your 4 links absolutely as efficiently as possible, even spread of traffic, very few wasted moments. It's quite simple for TCP to reconstruct what's gone on down that pipe.
Well, it's total sequence.
Right.
Yes, I got no out of order packets. So for a little bit of layer violation, routers are now looking at TCP headers, and UDP. A little bit of that, I get back an amazing amount of payback. How do we do these days 800 gig circuitry?
Well, you can't buy 800 gig things off the counter, can you? You have to buy multiples and gang them up together somehow.
You just said it. That's how we do it. And so a lot of this actually relies on this ability at the network layer to look inside the end-to-end transport layer and go, look, I don't want to be a meanie here. I don't want to be a bad person. I will try and keep sessions together so that I don't give you a flurry of out-of-order packets. And then we're cool, aren't we? And the answer is, well, basically, apart from a few folk bleating in the corner down the back of the room going, no, I'm not happy.
I'm not happy. I wanted all of it. I
wanted all of it.
Can you do better? I mean, that's the golden question, right? Is there a moment out there where we could do better?
Well, this is the issue of where do you want to do it? And by where, I mean network, transport, application. Of course you can do better. You just got to look at the right spot. And in this particular case, if you're using TCP, and you really want to get much greater bandwidth across some of these scenarios, you use a very elegant, and I'll call it a hack, but it's actually an elegant piece of engineering called multipath TCP.
So we were on equal cost multipath IP, and we are now on multipath
IP.
Multipath TCP.
Right, where I establish multiple TCP sessions between the same 2 endpoints. Now, they'll have the same source and destination IP, whoopee-doo, but they'll have a different port number of those pair of ports. That's how you distinguish them. So I get a session to you with port 1, another session with port 2, another with port 3, up to port 128. Who cares?
Yeah, it does not have to be that the port numbers are in a sequence. That is not part of the magic sauce here. The point is that there are 4 things each of us know is the other party, and if we talk into them, the other party gets what comes out. But Geoff, these are TCP sessions, so each of them is a reliable stream of bits, and I've now got to divide what I want to do into those 4 things, right? I mean, am I having to consciously chunk my stuff up into this? How do I do this?
Yes, you are going to chunk your stuff up, and you're going to assign a chunk down a path. And so you've got independent TCP control sessions, and of your data, you chunk it up and you assign a chunk to a single path. And that works actually better than you thought, much better than you ever possibly could believe. Why? There's this thing about TCP and friendliness. You see, what TCP tries to do when there are multiple independent TCP sessions, let's say there are 20 of them, is to equilibrate amongst them such that each independent TCP session gets its fair share, 1/20th of the bandwidth.
Yeah, now there's a twist here we've talked about a few times on ping, that really depends on all the TCPs having a similar idea of what fair means. But let's push that to one side.
Let's push that to one side.
Now that they all agree about what fair means, they do a fair shares div between them.
And with my single path TCP, I'll get 1/nth of the common network resource, tops.
Yeah.
With 2 TCP sessions, I'll get 2/nths.
Because for the network, it doesn't know that these 2 things correlate. As far as it's concerned, it's got to work with you, TCP, to make fair shares happen, so you get 2 of the units.
And in fact, it's not a conversation between me and the network. TCP fair sharing is a conversation between me and all the other TCP sessions. So if I can exert more pressure on the network, I get more value. And by having 20, 100, 1,000, multiple TCP sessions, I'm the bully in the block. I'm pushing everything else to one side. So not only does it kind of get me around this issue of I can only go the speed of a single path in a multipath environment, I can actually dominate the multipath environment. Woohoo! And there's no way the network can actually arbitrate that without introducing more complexity.
Right, but I've now got complexity. So I want to send 2 gigabytes of buffer to you, and I've constructed 4 TCP sessions between you and me. What tricks have we got on the shelf that will allow us to divvy these up amongst the TCP sessions? Do we do a version before pushing it out to TCP of that trick you were doing, hashing on values and using the bottom bits as a distribution across the paths? How do I manage this, Geoff? I've got to do it.
Oh, but now you can actually do this in much the same way as BitTorrent works. A file is just a sequence of blocks on a disk. And let's think of it as a queue of transfer requests. Each one is a standard size, whatever the size of the file system might be. Let's say it's a kilobyte. So there's a queue of 1 kilobyte requests. Now I have 10 multipath TCP sessions. So I assign the first 10 blocks to the first 10 TCP sessions. Off we go. Yep. First one to finish its block gets the next block. The second one to finish gets the next block. And so I don't predetermine which block goes through which path.
Right.
If the path is awesomely fast, it gets more blocks. And if one path is awesomely slow, it gets far fewer blocks.
Right. And I've sat watching the visual display of how your blocks are moving in a BitTorrent type situation. I use it to download ISO images when I'm doing operating system upgrades. And it's kind of a weird spattergun of blocks being sent. It's not a linear order. So it fits the file model, Geoff. I'm on the presumption I need all of the file to get my job done. But there are use cases in data transfer where this isn't necessarily a brilliant fit. Sometimes you want to work on partial content and you've now got to back off and think, okay, I've got limits on exactly what partial means here, because if you want to work on the first 10 gig of this file, I can't randomly send all of the back of it. I've got to know that that's what you want to do. So there is a bit of kind of application awareness complexity that comes in here.
Right, but it certainly solves a problem, doesn't it?
Oh my goodness, I'm getting this file through 10 times faster.
Exactly. For a particular class of problem, by utilizing the application layer, you can put more pressure on the network layer to actually improve your position. Against everyone else, might I add, but yes, improve your position.
Is this a theoretical model or is this something people actually went out and coded?
Oh, people have coded. Multipath TCP is out there in the RFC standards. There are implementations. I dare say if you fossick around, you'll find it certainly for things like Linux. It was said that Apple implemented it for Siri. And I remember looking at Siri with a packet tracer and actually saying, yes, Siri was implemented using TCP multipath. Bizarre.
I think I remember a conversation with you about how quickly Apple were able to ship downloads to people. And it looked like if your handset, your phone, knew it had both Wi-Fi and cellular, they were doing some things to use both channels simultaneously to fetch those assets.
And you're willing to, if you will, tell the device that the cost was the same in dollars.
Yeah.
Use them both. And as soon as you could say that, use them both, I can actually use the Wi-Fi and the cellular data connections and run the two together. And just simply whatever's fastest gets more data, but I can use them both at the same time. It's quite clever.
Wow. So this is not a theoretical thing. This is out there in the world as a real way of using more bandwidth underneath you.
It didn't get an awful lot of traction. Siri was almost the only app that used it in the Apple ecosystem at the time. I'm not sure it's expanded any further, but it's sort of an interesting case in point. But I want to progress the story.
Oh, there's more.
Oh, God, there's more. You see, the next thing to come along, and it's now been 10 years, is Quick.
Right. Quick being another mechanism to get reliable bytes between things, but it's kind of not TCP, is it?
Well, it's TCP hidden inside UDP through encryption. So what you actually see is just a set of UDP packets. You can't see the TCP control systems. It actually has the support for having multiple TCP, but it's all inside one single UDP flow state, right?
Yeah, but UDP is not TCP, Geoff.
How do you load balance quick?
Well, UDP is not TCP, so you can't do the trick of using packet tricks in TCP-specific ways to get reliably the same TCP session down the same path, all the TCPs inside this UDP. So yes, Geoff, how do you make this fly?
It's really hard because all the embedded TCP sessions inside your quick session fate share. All of them fate share down one path.
This isn't sounding good.
Well, it's kind of a bit of a step backwards because, again, many things are trade-offs here. And by deliberately not exposing your structured flow information to the network it just cannot do compensation for multipathing at the network level. It can't. All the packets with the same UDP header sort of set go down the same single path. You go, well, okay, I can live with that. The answer is, can you?
Sounds like we've just decimated the available bandwidth for me as a consumer. The greater good outcome might be all these UDPs are equipoising and the network providers balancing them over links, but I'm not seeing the benefit as me as an individual.
That's kind of where it's heading, isn't it? And it is a bit of a to and fro between what you expose to the network and what you get as a benefit back from the network. But the issue is, quite frankly, you and I aren't given a say.
Wait, what? Hang on. What do you mean?
Your browser, statistically made by Google, called Chrome,
yes,
that's
true,
is making decisions on your behalf along these very trade-offs and seeing what's best for you. And you don't get the levers. You don't get anything of that. They don't.
Right. So there is a sort of fantasy that we have a degree of control over these decision logics on how things are done. If you are a technologist, you can probably write systems to exploit this. But in the general, ordinary case of applications on phones, tablets, laptops like this, it's not my call. It's some intermediary writing code, deciding how they're going to package it. And if they decided quick is the one, I'm not getting any multipath outcomes from what you're saying. There isn't a wait, there's more moment here, is there, Geoff?
Not down this particular path, no. As I said, I think there's this trade-off around, we've decided we can't keep on increasing the clock. Clock speeds haven't gone any faster for decades now. And so the way we get more capacity out of the network is by going seriously parallel, seriously. The other part of this, though, is also a look at how we do routing protocols, because that's the other problem inside all this space. The conventional view of a routing protocol is there is one single best path.
Yeah.
What do you mean? So imagine, peak hour, and everyone's going back to their house. And they all live in the same spot for some reason. So what routing says is you're all taking Freeway 101. But there are other ways to get there. So what? Routing says there is one best path. That is the best path. But it's clogged. It's full. No, routing says...
Do you remember the time you, me and Paul were going to IETF in San Diego? And Paul said, let's drive. Then he couldn't go. We wound up with a car on I-405 in rush hour. And once you're on it, you can't get off it. You are basically on that road crawling at 10 miles an hour until you get to San Diego. What a road trip.
Well, that's what routing does to you in packets on networks. They don't have any feedback as to what's the best path. There's no Google map view. There's no outer level that says, that road is completely congested, take another path. Routing can't do that.
Current routing, the way we use it right now, BGP routing, doesn't do that.
Oh, every attempt to try and fold that kind of load feedback, and I'm going way, way back to the mid-'80s with the Hello routing protocol and similar, where you tried to sort of include a factor of its loading and efficiency and give you a routing system that was a path that was the best path on the day at the time, that second.
Yeah.
Again, the problem is feedback. Hey, everyone, use I-102. Oh, shit, everyone's using 102. Hey, everyone, use 101.
Yeah.
Oh, God, everyone's 102, 101, 102, 101.
And we do actually sometimes see in BGP evidence of people who are using some kind of weird traffic management framework. So between 10 and 2, they do pattern A, and then between 2 and 4, they do pattern B, as if someone is actually changing the levers, cranking it to try and make a marginal benefit on it.
It's been observed many times that amongst the lists of the most dynamic BGP updaters, the folk who spend all their time updating their BGP routes, a lot of it is attributable to the so-called route optimizers.
Yeah.
Unless you've got your feedback loop tuned really well, and most of them don't. As soon as you push traffic one way, that creates traffic, and that then means you push it another way, and that creates traffic, and so on and so forth.
Yeah.
Nothing is stable.
So we've had this beautiful conversation about the ways you can multiplex up multiple things to get an efficiency gain and achieve something close to the best possible bandwidth between 2 points. And you're now saying, because of the way we do BGP and the idea of best path as a single thing, we can't do that in the routing plane. We've got no trick in the armory to make routing share load across 2 links that might otherwise look like really good choices, because we select one of them as best path. Well, what are we going to do?
I actually think the answer lies in this area of quick and TCP multipath. And I suppose the observation is a pretty simple one. Think of the amount of silicon processing per packet. In my end device, in my laptop, it's a supercomputer. It has an enormous amount of processing capability, and its packet rate is not that high. I can do a lot of clever tricks at this end with my traffic, particularly if I've got choices in the way I can mark things. So if I establish 20 different sessions using, multipath TCP, I can play with stuff because I have the processing power to do so. What about inside the network? What about in a router that has, 40 800 gig channels connected to it? You can't breathe. There's no oxygen. You are just panicking. The packet rate is so high, you've got about 2 cycles per packet, if you're lucky, to get rid of the bloody thing. You can't be clever in the core of today's networks. You just can't.
It's not the place to put these kinds of complexities into the story, is it?
Right. Your silicon is barely keeping, on par with fibre. And so all we do is just hunk in the fibre, parallelize it, hunk in dumb silicon, and do basic routing tricks with ECMP, and that's all you've got. And then basically hand the problem off to the edges of the network, saying if you really want speed out of this, you need to be clever. The network isn't going to do it for you.
But you're kind of hinting at the possibility that with a little bit of knowledge about path diversity exposed to an application, and for the right kind of traffic behavior, I could chunk what I want to fetch into 4 different IP sources, which I know lie on diverse paths. And I could play this game a bit like BitTorrent does with multiple sources for the hashes and get the benefit of discretely different paths if I'm prepared to do a little bit of work.
Did we ever talk about explicit congestion notification?
We might have talked about that recently, Geoff, yes.
So here's a signal coming back from a path and a session that says, the path you've chosen is getting a bit busy, and if you continue to do this, I'm going to drop a packet. That's what the bit is saying. And if you fold ECN with multipath, and if you make a large and diverse collection of paths, you can actually, and if the network is actually doing ECN, you can actually get a decent stab at this kind of highly adaptive endpoint, where it's actually the end host that's doing all of the work in trying to optimize its performance through a network that has considerable diversity. If I'm the end host, brilliant. Nothing could be better. If I'm the poor benighted network operator trying desperately hard to minimize my bills, maximize my throughput, whoops, I've just handed the keys of the car to the application, to the host.
Yeah.
I don't feel very good about that.
No, it's an interesting question. Who's in control of this bus at this point? It's a bit like there are many hands on the steering wheel, Geoff.
Oh, I think there's only one. And as usual, I'll end it by saying everything is answered with money. The richest people on the planet these days build the end systems. The Googles, the Apples of this world, the Chrome and so on. The folk at the application level of the stack are in the driver's seat.
Yeah.
The network operators are being hit around the face with wet fish continuously with every new shock. And it's a sad life. it is a sad life, but, that's the way it's panned out. We kind of put the power at the end point. So that's where we're living.
Not a bad place to be in some ways. I'm surprised by how complex this story of doing things in parallel gets, Geoff. That's been really fascinating. Thank you.
Well, thank you. And dear listener, if you've listened this long, thank you for your persistence.
If you've got a story or research to share here on Ping, why not get in contact by email to ping@apnic.net or via the APNIC social media channels. Also, remember the Measurement at apnic.net mailing list on Orbit is there to discuss and share relevant collaborative opportunities, grants and funding opportunities, jobs and graduate placings, or to seek feedback from the community on your own measurement projects. Be sure to check out the APNIC website for all your resource and community needs. Until next time.